All right. We are starting our next unit, and our next unit is on what we call kinetics and equilibrium. And basically, what we're doing is we are moving a little bit past our thermo. So remember that our thermodynamics was there to tell us if a reaction was going to occur or not. And so now, if we know a chemical reaction is going to occur, we want to basically see how well does the chemical reaction occur and how fast does the chemical reaction occur. And in order to do that, we have to basically be able to look at the steps or the mechanism, what is actually going on when a chemical reaction proceeds. And so today is our first unit, or the first section in this unit, and we're going to focus mainly on what is going on in order for a chemical reaction to occur, and once it does occur, what can we do to speed it up? So we call this the collision theory, basically. So let's switch over to notability really fast. And when we look at notability here, we're looking at what's known as the collision theory. And the collision theory basically states that in order for a chemical reaction to occur, they have to actually collide. Big surprise there. So let's take a quick look at this slide where we have a bunch of molecules flying around and colliding with one another. Now you'll notice along the top, this is basically a setting where we get the perfect collision. We have some atoms here and some atoms here. They're diatomic molecules, so we see some nitrogen and some oxygen. And you'll notice right here when they collide in a way that allows the proper atoms to come into contact with one another. If you have bonds forming, we know that we have to have electron clouds overlapping with one another. So if we look down in the second example right here, if that molecule rotated a little bit, so they hit perpendicular to one another, this guy in back is never going to be able to have his clouds overlapping with this one right here. And so this chemical reaction can't occur. Just through random chance, it's a bad collision, it's not going to work. Now, also, in addition to getting this perfect collision that's occurring with this proper orientation, they also have to hit with enough energy to actually break the bonds. Now, when we're looking at our molecules, we know from thermodynamics that some atoms are really stable and some atoms are not. So if an atom is not very stable at all, this collision doesn't need a lot of force. If we look at this and we say, hey, you know what? This had like an enthalpy, a delta H of formation that was really positive. It's probably unstable. And I gave you the example of like blasting caps, mercury fulminate. If you just hit it with a hammer, boom, the thing explodes. Versus water has a really negative number and it's super stable. You could hit it with a hammer all day long and it's not going to do anything. So when you have unstable chemicals, the amount of force that we need in this collision is going to be less than if you have something that's really stable, but there is a specific amount. Now what we do is we've learned to sort of track these changes using what's known as a potential energy diagram. Potential energy diagram. And you'll want to take some good notes on this here. This is what we'll be doing in our homework, is labeling and drawing these diagrams. So for this, we have a graph. That is a horrible graph. I'm sorry, I can't live with those crooked lines. We're going to go ahead and get a straight line here, and we're going to get a straight line here. And we know that in chemistry, there's two situations. You can have something that's positive or you can have something that's negative when we are talking about its energy exchange. Is it gaining energy or is it losing energy? So basically, we start with reactants. And so we're going to start right here. These are my reactants. And basically, this is the energy of my reactants. So basically up here, this would be high energy. Down here, this would be really low energy. And so I just picked something that's kind of right in the middle. Now, in order for a chemical reaction to occur, remember if we look back here, we have to have these molecules collide with one another. There has to be some input of energy, and if It's unstable. It just needs to be a little bit of energy. Maybe it needs a lot of energy. But this is like if you're going to start a fire, you need a spark for that chemical reaction to proceed. So that spark is that collision, that input of energy. So all of a sudden, if the reactants normally have energy right here and I put more energy in, what happens is we get sort of a peak that pops up. And there's a special name for this. This is called the activation energy. So this is basically right here, and we abbreviate that E sub A. But we can call this the activation energy. Okay, so the activation energy is the energy that we need to get this thing going. And you'll notice right up here, we've reached a peak. What we've done is we've slammed these two things together with enough force to create some new bonds. And we're basically looking at this substance that's formed right here. And at this point, we still have bonds here and here. We also have bonds forming here and here. So we get this weird sort of intermediate. It's not a diatomic and a diatomic. And it's not this new chemical yet either. It's this hybrid, this sort of foursome that's stuck together. We call this the activated complex. And it's just sort of a temporary, intermediate, blink of an eye, it forms substance. Now, once this activated complex forms, it explodes and it blows apart into its products. Now, if it's an endothermic reaction, you're going to see a gain in energy. If it's an exothermic reaction, you're going to see a loss of energy. So let's look at what an exothermic would look like. All of a sudden, if my reactants are here, I need to end in a place, if it's exothermic, that has less energy. We should be losing it. So this is going to come all the way down here before we reach my products. And so we'll notice that now my products have less energy. So the difference in these two values, so whatever this is on the graph and whatever this is on the graph, that is my delta H value. And this is going to be a negative because products minus reactants is going to give me a negative number here. So this is my heat that's being exchanged. This is my enthalpy. Now this energy, we have a special name for it. We call it the potential energy. All right, the potential energy is the stored energy inside of the bonds, and that's what's being released. Now, what's sort of a new concept for a lot of us is going to come right here. You'll notice that my products have a certain amount of energy. I could technically force a huge amount of energy into this and recreate my reactants. I could get this reaction to go in reverse if I provide enough energy. We could see that energy requirement is really, really large, so it's probably not going to happen, but it is possible. Maybe not in this example, not probable, but possible. So there is actually an EA reverse. Okay, the possibility of reversing a reaction. And this is what we call a potential energy diagram. Now, if this was an endothermic reaction, it would have looked very similar. So this would be my potential energy over on this chart here. We would have my reactants starting right here. I'll just put R for reactants. We're going to have some type of activation energy. So the EA forward is right here. And we have our activated complex form. But this time, it's going to start to fall back down. And then, oops, I didn't mean for that to do that. So it's going to fall back down and then stop. So now you'll notice in this situation, my products have more potential energy than my reactants do. And so in this situation, my delta H is right here, and it's positive. So this is exactly what we want to be able to look at on our today's homework. We just want to be able to label these graphs and understand what's going on. Is it taking in energy? Is it losing energy? What are the energy requirements? So sometimes we'll have numbers on there, and we might get something like this. Draw a potential energy diagram using the following values. So this doesn't need to be exact, okay? It doesn't need to be to scale or anything. We just want to get a general idea. So I'm going to put potential energy over here. And really, I didn't label it in the other ones, but this is time. So over time, what is the amount of energy that's in our molecules. So this is telling me that the potential energy of my reactants is 50. So I'm just going to put a line right here and just say, hey, you know what? That's 50. And this is my reactants. Then I see this guy right here. Right? So that was the potential of my reactants. I see that EA is 15. So that tells me that I'm going to go up right here. This value is going to be 15. So when I reach the activated complex, it's pretty easy to get that calculation. I was at 50, I'm adding 15, so now I'm at 65. Now the question is it going to stop here, or is it going to come all the way down here and be either endo or exo? And so to figure that out, we have our delta H. And our delta H says that it is a negative 10. So this is exothermic, so I need to end down here. So this is going to come down, and this is my products. And then I know the difference is negative 10. So if I was at 50 for my reactants, my products have to be 10 less than that, so we would say that this is 40. And if asked, if somebody says, hey, what would it take to turn those products back into reactants? Well, we'd have to say, well, what's the EA reverse for this? So the EA reverse, if we were at 40, I know my activated complex is at 65. This must be equal to 25, right? Because 65 minus 40 is 25. So this is exactly what I would want you guys to be able to draw. Now, once this reaction is going, there are some things that we could do to speed it up. Sometimes the reaction will work, it's just really, really slow. And so we actually have a whole list of things that we could do to speed up chemical reactions. And so I've got this list right here. And what I've done is, rather than spend a whole bunch of time talking about all this, there's a really neat video that I usually show in class. It's a real quick YouTube video. And I'm going to provide the link for that. And it's going to kind of walk you through each of these in a really simple, easy way to understand it all. But a couple of things that I want to point out that they don't talk about. The first is number one, they don't talk about the nature of the reactant. And what I mean by this isn't something that you could really change per se, but I want you aware, if something is ionic, you are dealing, with pluses and minuses. You don't have to actually get things like this to collide. If you get a negative and anywhere in the same proximity as this positive, they're going to attract one another, right? It's not like a covalent bond where the clouds have to overlap. So ionic bonds, they're fast. They're really, really, really fast. When we're talking about all of this stuff, it's all about covalent bonds. That's what we're talking about. Now, concentration, molarity, stuff like that, they're going to talk about that quite well in the video. Gases, I wanted to make a note here, are the only things that are going to be affected by pressure. And then finally, a catalyst, I wanted to mention this with regards to the diagrams we've been drawing. When you are doing a potential energy diagram, what a catalyst does is it lowers this activation energy. So instead of saying, okay, this needed 40 to go, how long does it take for this reaction to absorb 40 energy, right? Maybe it needs to sit on the stove for an hour. So before this reaction can go, you have to be patient, you have to wait, you have to dump all this energy in. If you add a catalyst, you drop that requirement, maybe it's only 20 now. And so it's going to actually go faster. So when you lower this activation energy, you make the reaction have a much easier time to get started, and so it's going to go a lot faster. Also, for this section, generally this is something that I would have done a lot of demonstrations in class for, because it's fun to make reactions go faster. And one of my favorite things to do is to mess around with the surface area. So I actually am including 2 links to some videos that are showing demonstrations that I normally would have done in class. So I really recommend that you give those things a watch. They're pretty cool demonstrations and they're pretty fun to do. So with that being said, I hope this helps you guys out. Please make sure that you reach out to me and ask questions if you have any. And the worksheet should be posted It's a go formative lesson, so really you're just, putting in A and B and C for a lot of these, so it should be quick, simple, and fast. Hope to talk to you guys soon. Have a good one.